This Airfield electrical troubleshooting tutorial is designed to help qualified airfield lighting technicians to better understand how to troubleshoot series constant current lighting circuits. It will focus on three main points: finding a fault, testing a transformer, and finding an open. Finding a fault on the airfield is one of our most basic troubleshooting tasks. It's pretty simple to do, but there are some procedures that can make it much quicker and easier. Before I start talking about troubleshooting these circuits, I need to stress the importance of locking them out. If this circuit is energized while you are working on it, there's a good chance that you will be killed. It's that serious. You have to lock them out and make sure that the circuit you are working on is indeed the circuit you locked out. Here's an example of a situation that you might find on your airfield where you know you have a bad circuit. So you lock the circuit out, go to the S1 cutout and check it with a megger. In this case, the megger reading is 200 kiloohms. So it's time to go to the field and try to find it. The best place to start looking for the problem is at the midpoint of the circuit. So open the connection and connect one of the megger leads to one of the primary wires and one to the ground wire. Here you see the 200 kiloohm reading is indicating the fault is in the direction of the wire you're testing. From the same midpoint, you check the other wire and find that it has the same reading. What's going on here? Do you have two identical faults? No, the reason for this is you forgot to pull the S1 cutout cover and you're reading through the regulator all the way around the circuit to the same fault. In this situation, you have no idea which way to go to find that fault. So to find a fault, it's important to create an open circuit somewhere. This is best done at the S1 cutout. With the S1 cutout cover removed, the reading changes to a much higher value than the fault you're looking for. And remember, you're looking for a 200 kiloohm reading. Don't be distracted by other readings. This meg reading has really very little value at this point other than the fact that it's not the fault reading you're looking for. So the fault is not in that direction. So now with the S1 cutout removed, we know that the fault is in somewhere in the upper half of this circuit, and we have essentially eliminated 50% of the circuit by making one test. The next move is to move in the direction of the fault and go to the midway point and split the circuit again. Check both directions. By doing this, we're able to eliminate about 75% of the circuit with only two tests. So now we know the fault is in this quarter of the circuit. And we break the circuit again, and at this point, 85% of the circuit has been tested by only doing 3 tests. We might have to keep zeroing in on it. It may take several more tests depending on how many lights are in that portion. But you can zero in on it very quickly if you very carefully split the circuit in half each time. There's a unique situation that happens with series constant current lighting circuits which can be useful in troubleshooting, in which when there are 2 solid faults, the current will jump out of the circuit at one fault and follow the ground wire or a conduit until it jumps back in at the second fault, bypassing the lights in between. This creates lights out between the faults. Now this situation makes it easy to identify the fault locations. Simply mark both ends of the lights out section and then look for the faults there. There are times when this double fault scenario can be used to our advantage. In some situations, a single fault can be identified by intentionally creating a second fault and then following the lights out to the original fault that we were looking for. Now this doesn't always work. it requires a very solid second fault. But in many situations, it can be worth trying, and it can save you a lot of time if it works. There are two methods that you can use to ground a circuit in order to create a second fault. The first is a field grounding clamp. And this is a homemade contraption that is simply a male and female connector on a short piece of wire with a grounding lead connected to the center. To install this, you simply open a primary connection at a transformer and plug this into the primary line, and then you clamp it to your ground wire. Now I know this sounds crazy to people who are used to working with standard constant voltage systems. If you did this with a standard electrical system, it would make an explosion. But with a constant current series circuit, this is really no problem at all. And the other way to ground it is with a S1 cutout grounding cover. You can see the black cover on the left will ground out one side of the circuit, and the gray cover will ground the other side of the circuit. What we need to do is, for the first step, is to ground the circuit at one point, either at the S1 cutout or in the field. Here's a photo of a grounding cover installed on an S1 cutout. With this S1 cutout grounding cover installed, it'll ground one side of the circuit, and this will produce lights out between the cutout and the circuit fault that's on that side of the circuit. If we install the other S1 cutout grounding cover, it will ground the other side of the circuit, and we'll get lights out between the cutout and our fault on the other side. So using these two cutout covers, you can check first one side and then double check on the other side. You go out and you drive your circuit, and you're going to be able to identify which light, or possibly the wire between two lights, that is going to be where your fault is. Now again, this doesn't always work unless you have a real solid fault in the field. But especially in wintertime, it can save you a lot of headache opening a lot of cans. It's worth a try. So if you don't have a grounding S1 cutout cover, a homemade grounding clamp will work very well also. The way to install it is to, of course, lock out your circuit, go out into the field and break apart a primary connector at a transformer, install your grounding assembly and clamp it to the ground. Then go back to the vault, unlock it, and turn it back on. What you should see then is the lights out between the grounding clamp that you installed and the circuit fault in the field. Now this only works if it's a good solid fault, but it's worth a try. One of the problems that can cause a fault in airfield lighting is a failed isolation transformer. It's important to understand how to recognize these faults, how to find them, and how to test for them. Isolation transformers have a fairly simple design. They have a high voltage primary wire, comes in to the transformer, wraps around an iron core, and exits. Also wrapped around the same iron core is a low voltage wire which goes out to your light. The amperage and voltage is induced from the high voltage into the low voltage. They're completely isolated and insulated from each other. But if anything goes wrong, as you can see in the right hand picture, those wires are very close to each other, and so if there is a fault within that transformer, it will transfer high voltage over to the secondary wiring, and you will end up having high voltage going to your light. Now, this is actually fairly common, and it is very dangerous. So sometimes these faults are very obvious. Sometimes the signs of the fault are not very obvious, and quite often there are no visible signs on the exterior of the transformer at all. Regardless of how much physical damage there is to that transformer, The result is high voltage going to the fixture. This is very dangerous. If you were to pull this fixture with the power on, it's very likely you would be electrocuted. Here's an example of an isolation transformer that had no visible damage on the outside. When we connected a megger between the primary connector and the fixture plate, we got 0 megs. This is a dangerous situation because the fixture plate is directly connected to the 5,000 volt primary wiring. This is also a good example of how a field isolation transformer can give you a bad meg reading on your circuit. The fixture is bolted directly to the ground system, and the circuit is directly connected to the fixture. Here's a way to make your own test lead for testing an isolation transformer. It's made from a connector from an old fixture. Simply cut off the connector, strip the wires, and crimp on a ring terminal or just leave exposed bare wires on the end. Just plug this lead into the secondary side of your transformer and then connect your megger between the primary of the transformer and the secondary on your new lead. As you can see here, we have 0.032 megs across this transformer. This is a bad transformer. Another quick way to check a transformer in the field, especially if the can you're working with has water in it, is to set the transformer up on the drive pavement and then meg the circuit through it. Then drop it back into the can full of water and meg it again. If the meg reading gets worse, then the transformer is probably bad. This only works if the transformer insulation has been breached, which is often not the case. So you can't always trust this method, but it's a quick try. So here are some tips for finding faults. First, check your ALCMS computer or manually meg and record readings regularly. This will help you to see trends and events which can give you clues to what type of fault you're looking for. Next, know how the circuit runs. Look at the prints. Take them into the field with you if necessary. It's going to make it much less confusing for you if you know exactly how these wires are run. And if it's a solid fault, try the grounding cutout cover or a grounding clamp. This can make it easy to find a fault quickly. It doesn't always work, but it's usually worth a try. Next, test transformers before changing and discarding them on a hunch that they might be a problem. And with flush centerline fixtures, you want to look for test points for your initial tests. These are cans in which both feed and return are spliced. Breaking both the feed and the return make it easier to isolate the fault. And with these test points, you want to mark them by engraving TX plus the circuit number in the epoxy surrounding the fixtures. This will really help with future troubleshooting. And lastly, make sure to put the cutout back in the proper position when you're finished. Otherwise, the next guy along is going to have some problems. An open circuit in an airfield lighting circuit is a situation where a wire in the field has been parted or a connector has been pulled apart or burned open and there's no more flow of electricity through the circuit. This will result in the regulator shutting itself down and the circuit will be unusable until it's repaired. So because of this, open circuits are usually considered an emergency repair, especially if it's a circuit like a runway where you will not be able to use that runway until it's fixed. It's important to understand the logic behind looking for opens. It's the opposite logic of looking for faults. If you understand this, it's no more difficult to find an open than it is to find a fault. If you don't understand this, it's going to drive you crazy. So finding a fault is looking for a positive connection to ground. Finding an open is looking for a nothing, a non-connection to ground, a non-conductivity. And finding a fault uses a megger to break through the weak insulation to go to your ground. Finding an open uses an ohm meter. All you're looking for is non-conductivity. In finding a fault, you create an open by pulling your cutout, and then you go towards the fault. Finding an open, you need to create a fault and then go away from the fault. I'll try to describe how this works in the next slides. If you pull your S1 cutout and put an ohm meter on your lines going out to your field, and you check your resistance in that line, you're probably going to get about 15 to 75 ohms on most circuits, depending on the size of the circuit. In the case where you have an open, if you check across your lines going out to your field, you should max out your ohm meter. You'll have no continuity in your circuit going around the field. After you've tested your circuit, you know that you have no continuity in your wire. The next step is to ground it somewhere. This can be done either at your S1 cutout by turning the cutout cover to the left and reinserting it, or it can be done out in the field with a homemade grounding connector assembly. It's important to note that when looking for an open, you do not remove the S1 cutout as you would with looking for a fault. If you remove that S1 cutout, what you've done is created another open. So with two opens in the system, it is going to be extremely confusing, and it's going to be very difficult to solve your problem. Okay, in this scenario, I'm using the S1 cutout as my grounding means. The next thing I want to do is go out to the midpoint of my circuit. I want to break the wires and hook up an ohm meter between one of the wires and the ground and test for continuity. Now, in this scenario here, I've put 0.00 on my ohm meter. It probably will not be 0. It will probably be something greater than that, but it will be an extremely low ohm reading. So you can see in this direction, I have continuity going back to the cutout. However, when I check for continuity on the other wire, you'll see that I have no continuity. I'm maxing out my meter, an extremely high ohm meter reading. That means the open is in that direction. So just like in finding a fault, I've now eliminated half of my circuit by just doing one test point. So our next move is to split the circuit in half again and test for continuity. Here you can see that I have continuity between this point and this S1 cutout. So by doing two test points, I've eliminated 75% of my circuit. We now know that our parted wire is in this 1/4 of the circuit. So the next step is to go to the midpoint of the remaining circuit and test again. In one direction, we're going to get continuity to ground, and in the other direction, we will get no continuity to ground. And we keep going towards the no continuity until we find our problem. So you can see with 3 properly placed tests, we can eliminate 85% of our circuit. If we just continue eliminating by cutting the circuit in half, we can very quickly isolate down to where we need to be. Here are a few tips for finding an open. First off, focus on the open only. This circuit is going to be completely unusable until the open is repaired, so that should be your main focus. Don't be distracted by faults or transformers or anything else in the circuit. Next, know how the circuit runs. Look at the prints, maybe take the prints with you. Another quick check that might save you a lot of time is to look in the cutout cabinet and make sure the S1 cutout is in place. It could be that the previous crew forgot to put the cutout back in and you're now seeing an open. Once you've determined that you have an open, you need to get out there and drive the circuit first. You need to look for something obvious, such as construction workers, or maybe earth moving equipment. Opens rarely happen without human involvement or error. It can happen that a wire burns off clean in midair, but it's very rare. Usually it involves someone out there doing something to the circuit. Now, if someone is working on the circuit and you start manipulating the regulator, you could kill someone. So it's very important. Check the circuit out and clear it first. Now, another good thing to look for is overheated cans and lids. You can go out and drive the circuit, especially in winter. Look for melted snow on a lid, and that could be a telltale sign, and it can save you a lot of time. So don't get distracted by non-open circuit issues. Don't mag the circuit. That's not going to help with an open. Don't waste time looking for faults. And don't bother replacing transformers. A bad transformer does not create an open. Make sure you reconnect and close all test sites as you proceed. That's very important. If you're creating more opens as you go along, it's going to get more and more confusing. And finally, when you're done, make sure to put the S1 cutout back in its proper position when you're finished. Otherwise, the next guy that comes along is going to have a problem. And lastly, some very important things. Think first, lock it out, and make sure you go home after work. Have a good day.